Hello everybody, welcome to another little episode of Mr. Dwight Doodles. This time around we're going to be locked in with some chemistry. If we look at our paper 1 passport to success, we're looking at reactivity on the groups 1 and 7. Let's dive straight in, ladies and gents. Bonding and reactivity. Now, the good thing about chemistry is that C1, C2, C3, C4, they all just link together. So as I go through this question to try and explain it, I'm also going to be doing some doodling so we can see. Calcium reacts with chlorine to produce calcium chloride. Explain. We've got to state and we've got to give a reason for. What happens to calcium atoms and to chlorine atoms when calcium reacts with chlorine to produce calcium chloride? So we've got to state what's happening to these atoms and give a reason for it. So first off, I get myself, and I know that you've seen this little bad boy before. This is the periodic table. There's our key. This gives us everything we need to know. So we're talking about calcium and chlorine. Here's our calcium, just here. Calcium. So let me write these numbers in. Calcium has an atomic number of 20. So that means it's got 20 protons and it's got 20 electrons. If we go to chlorine, on this side, you can see it's got 17 protons and 17 electrons. So this is our calcium. This is our chlorine. That's got 17 positives and 17 negatives. So why and how do they bond? Firstly, there's 3 types of bonds. There's ionic, covalent, and metallic. And again, going back to the periodic table, you'll notice that the staircase here tells you that everything this side is a metal, everything that side is a non-metal. So we're going calcium metal, chlorine non-metal, and this is an ionic bond. So what happens is this. It's got 20, so it's got 2 in the first shell, 8 in the second shell, 8 in the third shell, and in the fourth shell, it has 2. So I'm just going to draw those 2 as little circles. They're known as dots. I'm going to come over to my friend chlorine here. It's got 17, so it's 2 in the first shell, 8 in the second shell. I should do this here really. So it's 2, 8, 8, and then 2, 2, 8, and 7. So let's pop this here. I'm going to do this with crosses. 1, 2, 3, 4, 5, a 6, and a 7. What happens next? Well, this is the explain part. This electron here will go and sit over here. This is known as a dot cross diagram. So we put that into words. So calcium loses 1 electron to 1 atom of chlorine. Now what happens here is it's not 17 anymore. It's now become 18. So chlorine has an overall negative charge of 1. 18 minus 17 is 1, so it's minus. The problem we have is that this little chap down here, this electron, still doesn't have a home to go to. So what we do is we introduce another atom of chlorine. There it is. And so this then down here, and on it goes. So when we write the ionic formula, calcium has lost the 2 electrons in its outer shell. So 20 is now 18. 20 minus 18 is 2. So we get calcium 2 plus. How many calciums are there? Well, there's only 1 there, and it's Cl minus. But look, we've got 1 and we've got 2. So we stick a little 2 there. That is the ionic formula. Now what that creates, so with 4 marks here, 2 electrons to 2 atoms of chlorine. But what happens when they become charged is these atoms are now ions, hence ionic bonding. And before we look at B, which is why is chlorine more reactive than bromine, I'm just going to sidestep. So once we've now made your calcium chloride, you remember you need to know this diagram for ionic bonding. This is what we call a giant ionic lattice. Now they're ions, the calcium is positive, the chlorine is negative, and we get this opposite charge effect, like so. Ionic giant lattice. Out the way, cable. This is a force, I hope if I could spell it right, and it's called the electrostatic force. It is opposite charges attract, and it holds the arrangement in this giant ionic solid. Therefore, what are the properties of giant ionic solids? There are many electrostatic forces, which means that it is strong. Now, in order to turn that solid into a liquid or a gas, you would have to transfer immense levels of energy in the form of heat in order to break the electrostatic bond. Hence the property high melting, high boiling points. If I deviate somewhat and we talk about a covalent compound, there's my blue pen. Let's change it up, ladies and gents. So let's go with water. So with water, we've got H2O, hydrogen oxide. This is not an electrostatic force, this is a covalent force. This is a covalent bond, which means that electrons are shared. So hydrogen and hydrogen. Now if we go back to the periodic table, there it is, look, and it has an atomic number of 1. That means hydrogen has 1 electron. There's 1, there's 1. What it wants to do is fill its outer shell. Because it's got 1 shell, in order to fill it, it only requires 1. And the oxygen atom shares those. But if we look to oxygen, okay, has an atomic number of 8. It's in group 6, which means it's got 6 electrons in its outer shell. I've drawn 2. 6 minus 2 is 1, 2, 3, 4. Now, if we add them up, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is, I'm dread to say the word happy because it's not, it doesn't have feelings, but it has a full outer shell. Hydrogen has an outer shell that is complete with 2, and so does that one. That's a covalent bond. Now, I'm now going to help understand a somewhat easy but challenging concept. I'm only going to draw this like this now because it looks a bit easier. So there's our water molecule. If I now add that water molecule to another water molecule, I'm sorry, silly me. Let's do it here. Right, there it is. So let's add another one. What happens is when you turn water, well, water's in the liquid state. So what happens is a force holds them together. This is not an electrostatic force because there is no charge. This, because these are molecules, and you've got 2 molecules and it's in between molecules, it is known as the intermolecular force. So therefore, giant covalent structure, high melting, high boiling. Why? Lots of electrostatic forces that are strong between opposing charges. You need a lot of energy in order to break those bonds. But if we look here, in order to take water in the liquid state to turn it into a gas, you just need to break that intermolecular force. So the amount of energy required is much less in order to change its state. Hence, these molecular substances have low melting and low boiling points. Remember, that is a covalent bond. When you add heat, it doesn't break the covalent bond. Hydrogen still is connected to the oxygen. What happens is it goes from a liquid that's held together by an intermolecular force, and you break that force. Obviously, when it's a solid arrangement, there are more of them. Therefore, to go from a solid to a liquid, it does require energy to break those intermolecular forces. Right, let's jump back to a bit of reactivity. Explain why chlorine is more reactive than bromine. Get yourself a little P table. Here it is. There's chlorine. There's bromine. So one is above the other. Little technique now. If you look here, period 1, period 2, period 3, period 4. These refer to the number of shells. This refers to the number of electrons in the outer shell. So we're dealing with 7. But chlorine has 3 shells and bromine has 4. So both of them, actually do a little doodle here. So 1, 2, 3, and 4. And you've got 7, 3, 4, 5, 6, and 7. That would be chlorine. But then, sorry, 4, that would be bromine. Apologies. Chlorine, 1, 2, 1, 2, 3, 4. 1, 2, and 3. 4, 5, 6, and 7. Now, 4 shells, 3 shells, both with 7 electrons in the outer shell. Because it's in group 7, what it wants to do, it wants to fill its outer shell. So in order to fill its outer shell, it needs one more. It needs one, both of them need one more. That's an electron. Electron is negatively charged. Therefore, there is a force that pulls the electron into the energy shell or electron shell and holds it in place. Now, if you just look at those lines, and if I was to bring my ruler out, and again, these aren't to scale, but that line is much longer than that line. Therefore, the distance is less. The force is greater, pulling the electron in. That line is longer, which means the force is weaker to pull the electron in. Also, the more shells it has, the more shielding takes place. So if you've got other electrons moving around, it will weaken the force. So explain why chlorine is more reactive than bromine. State both require one electron in order to complete their outer energy level or electron shell. Bromine has 4 shells. Therefore, the inner shells shield the outer electron from being pulled into that outer shell. And the force is greater within chlorine because it has less shells. I hope that makes sense, and I hope you enjoyed the little video.